In image processing, visual features represent specific characteristics or attributes within images that can be extracted, analyzed, and utilized by machine learning algorithms. Choosing the appropriate visual features is critical as they determine the ability of AI systems to recognize patterns, detect objects, or interpret images accurately. The effectiveness of computer vision solutions relies heavily on selecting features aligned with the application's objectives, computational capacity, and data quality, ensuring that the derived insights are accurate and reliable. Visual features can generally be grouped into several primary categories. Color features describe hue, saturation, brightness, or color histograms. Texture features capture smoothness, roughness, regularity, or irregularity. Shape features define edges, contours, and geometric structures. Spatial features represent positional relationships within image pixels or regions. Temporal features apply to videos, measuring changes or movements across frames. Each feature category has specific strengths, making them suitable for particular use cases in image processing tasks. Color features provide valuable information on the visual perception of images, frequently utilized for tasks like content-based image retrieval or segmentation. Key color features include color histograms, represent the distribution of color values. Dominant colors identify prevalent colors within an image. Color moments include statistical measures like mean, variance, and skewness. Choosing color features is beneficial in scenarios where color differentiation essentially determines class distinctions, such as identifying ripe fruits or classifying product images based on visual appearance. Texture features involve analyzing the surface properties and visual appearance related to repeated patterns within an image. Common texture-related algorithms include gray-level co-occurrence matrices. GLCM measures how often pairs of pixel intensities occur in specified spatial relationships. Local binary patterns. LBP represents local spatial patterns and textures efficiently. Wavelets and Gabor filters, useful for defining textures via frequency analysis. Applications of texture features are extensive in areas including medical imaging, industrial inspection, and natural material classification, significantly improving accuracy by recognizing subtle visual cues. Shape features center on recognizing and quantifying the geometric properties of entities within an image. Fundamental approaches for extracting shape features include edge detection, identifies boundaries between different intensity regions. Contour analysis provides information on object outlines or boundaries. Invariant moments offer descriptors unaffected by translation, scaling, or rotation. Shape characteristics are pivotal for applications such as facial recognition, object detection, and gesture analysis, where form and outline are significant identifiers. Spatial features relate to the position, arrangement, and distances between image elements, crucial for understanding contextual relationships within visual data. Key methods include spatial distribution descriptors, quantify spatial arrangements of colors or textures. Region-based features focus on local segments of images. Use of spatial features is prevalent in satellite imagery analysis, environmental studies, and detailed image classification since spatial context significantly influences interpretation accuracy. Temporal features cover dynamic changes across sequences of images or video frames. Capturing temporal features includes detecting motion trajectories, temporal intensity variations, and object tracking. Typical methods include optical flow, estimates motion between sequential frames. Motion history images, compiles historical movement data into compact representations. Temporal analysis is invaluable for industries where monitoring behavior, tracking movements, or understanding time-based patterns such as surveillance, traffic monitoring, and athletic performance analysis is required. Selecting visual features must align closely with specific image processing legal, technical, and practical needs. Considerations include application objective, determining features relevant to the task, data constraints, data availability, quality, and image resolution, computational resources, availability and constraints of processing capacity, and speed. Matching these elements ensures optimal feature selection, enhancing model effectiveness, accuracy, and applicability in real-world scenarios. An effective feature selection approach should incorporate several stages: data analysis, understand image characteristics and variability, requirement specification, clearly define the target and constraints, testing and validation, experimentally assess different features, selecting those demonstrating highest performance iteratively. Feature selection may leverage dimensionality reduction techniques or feature transformation algorithms, aiding in systematically narrowing down the optimal combination of attributes that meet the image processing task. Microsoft Azure offers multiple tools for selecting and extracting visual features effectively. Azure Cognitive Services Computer Vision easily implements common visual feature extraction practices. Azure Custom Vision allows for custom training and pre-processing to identify relevant visual features. Azure Databricks and Azure Machine Learning support advanced custom algorithms for sophisticated feature selection processes. These cloud-based tools simplify and optimize the visual feature selection process, ensuring accessible, robust, and scalable computer vision solutions. Selecting appropriate visual features encompasses specific challenges frequently encountered: redundant or irrelevant features. Choosing unnecessary features may degrade performance. Complexity. Complex image data frequently requires extensive experimentation. Computational overhead. Complicated features can increase processing time. Addressing these challenges involves leveraging techniques such as dimensionality reduction, feature subset selection, or algorithm optimization, ensuring efficiency and precision in selecting relevant image attributes. To effectively select visual features for image processing, the following best practices are recommended: clear definition of objectives, precisely establish goals to guide feature selection; iterative testing and validation, continuously assess feature relevance through practical experiments; balance sophistication and efficiency, ensure advanced features benefits justify computational costs; consider domain knowledge, integrate domain insights to select the relevant and impactful features. Adopting these best practices will reliably lead to the robust, accurate, and resource-efficient choice of visual features in computer vision tasks.